right. Today's not the day then.
They didn't get back to me.
All right. Well, yeah. Maybe follow me after office or after lecture, and then we can go and do some stuff. Yeah, I'm done for meeting. I mean, I have to scan the lecture notes and I have to post them.
Yeah.
So it'll be a brief meeting, but yeah, let's try today after lecture. Okay? We're both here already. Good work. Hey Taylor, what's up?
What time is that thing next week?
4 till 5.
4 to 5?
Yeah, 4 till 5 on Friday. And the thing is the Pi Day thing? The Pi Day training? Yeah. Yeah, 4 till 5. So Pi Day will be 3 till 4. There's going to be a bunch of Pi. Friday, March 14th.
Yeah, so we're doing 4 to 5 is the training thing?
Yeah.
What's the actual?
Sunday, March 23rd, 9 till 1. Yeah. So yeah. Come in to the training. I'm going to send an email about the training counseling this week. I'm going to go wash my hands before we get started. We're back. Hey. Hello, B42 folks. Good to see you. Hello. So good news. We have got the term test 2 grades are done, which is blessed. However, the deferreds have not been finished grading yet. Or sorry, because it hasn't happened. The deferred term test 1s aren't done, but the standard term test 2 is done. Okay, there we go. I haven't looked, I'm sorry. Yeah, the question was what's the average, and it's just I don't know. So with the end of week announcements, you can expect to get the term test 2 grade if you wrote the standard 1, but not if you wrote the deferred 1, because it hasn't happened yet. Okay. Okay, excellent. What are we up to? So I want to go back and redo this proof because I made a bad choice of notation that made it just look like really crazy and messy. We're then going to prove the classification of conservative vector fields, which is a really nice theorem, kind of a big. It's just a dark door. I don't know what's in here. Ah, I've got an urban explorer on our hands. Okay, nice. Apparently it's got bags in it. Okay, so we're going to prove the classification of conservative vector fields. If that doesn't take the full time, then the week 9 notes are already up. We'll do a little bit of week 9 stuff. That's going to kind of end off our rapid tour of vector calculus. Once we've got Green's theorem, Stokes' theorem, Gauss's theorem, we're then going to move into kind of the general framework that contains all of these theorems. So all of these theorems kind of feel kind of different, and the last part of the course is going to be about differential forms, which are a unifying framework for all of these things. Okay, so that's the plan. We'll see where we get to today. Yeah, let's check it out. Let's do some math. But actually, before we start, anything people want to check on? All right, let's do it. Okay, so last time we did this, we did it with really messy notation. Let's pick slightly better notation. So so we've got a vector field PQ0 on S. Now, since our surface lies in the plane, it has a really, really nice parameterization, right? How do we parameterize this thing? We just map it to itself. What a lovely parameterization. Okay, so what do? First off, we want to hit this with Stokes' theorem. Okay, so we following. Okay. And this is our setup. All right, so let's calculate out what these look. Oh, this is our surface area element. This is our line element, and that's going to be okay. Yeah, so let's calculate out what this thing will be. we take a cross product. Okay, and I feel like I'm off by a minus sign somewhere. No, we're good. Good. Okay. Now we need the surface area element. Okay, now our parameterization here is really nice. Our parameterization is just the thing itself, right? So this is going to be okay, so we can take following. Okay, so our parameterization is here. Okay, for the I component, we're going to get zeros. For the J component, we're going to get zeros. For the K component, we're going to get a 1. Okay, so putting the pieces together, okay, got something like this. And now when we take this dot product between these two guys, we just pick out the last coordinate, right? These kind of weird partial q, partial z, partial p, partial z's, those go away when we compute the dot product. And we get partial q, partial x, partial q, partial y, dx dy. Oh my goodness, that's Green's theorem. Right, and the right-hand side of this is equivalent to Green's theorem in the standard way. Right? We're just integrating around the boundary with our outward pointing normal. Things people want to check there, things people want to ask about? Yeah?
Why don't we need a counterclockwise parameterization? So why don't we need a counterclockwise parameterization?
Right, so yeah, so this thing, right? This guy does depend on the orientation of the boundary. Right, and the orientation that we pick for Green's theorem and for Stokes' theorem in both cases is this counterclockwise one. Right, so they match because of the way Stokes is set up. So, lovely, lovely. Okay, so Stokes, if we restrict it to the plane, gives us the same integrand as we had for Green's theorem, which is lovely. All right, onwards and upwards. Okay, where were we? So we've redone that. Okay, so this is the old version of that note, but the notation was crap. So get rid of that version. We'll replace that with this guy. Lovely. Okay, so this is where we wound up. So we did a integral using Stokes, where we got 0 each time. Then we got to where we want to switch to a surface integral, and we started the process of parameterizing. Good. We should probably get the surface component. Okay, so what do we do here? Okay, now we take our derivatives in the u direction. And then in the v direction. Okay, calculate out the cross product. Okay, so we want a 0 minus -1, so that'll be a 1. Then we want -1, but we want a minus sign, so we want 1. And then we want 0 minus -9. Okay. That stands to reason for a normal, right? Where this normal vector to our parameterization is the same as the normal vector of this plane. Right? We've got this plane, vector sticking out of it. Our parameterization should have the same normal vector as the plane, so things look good. Okay. Now we want to switch this vector integral to be an integral over this surface instead. Sweet. So we calculated out this guy. So then we are going to switch perspectives using Stokes' theorem, and to do that we need a curl. So we're going in that direction. In order to do that, we need curl of this guy. So negative y cubed, x cubed, negative z cubed. Okay, so let's get the curl of it. Okay, so what do we get? Taking this guy, we get 0 and 0. Again, 0 and 0. And then here we get 3x squared minus negative 3y squared. Something like that. Okay. Sorry, I should say more steps. Okay, so we take this dot product, only one of the terms is non-zero. Something like this. And now we have a bit of a mismatch in terms of our variables, right? We have that we're integrating x squared and y squared, but those are really things in terms of u and v, right? So coming back here, right, we want to integrate our x's and y's. Those are really u's and v's. Cool. Now we have a situation where we want to integrate 3u squared v squared, and our domain is now this disk. It's the base of this cylinder. So whenever we see such a thing, what do we want to do? We've got an integral over a disk. How do we handle such things? Yeah, we want to do like cylindrical coordinates, polar coordinates, that kind of thing. Cylindrical would be tricky because our tube is not in the same direction as cylindrical coordinates wants it to be. It's not parallel to the z direction. But yeah, we can do a polar coordinates thing. Good. And now this is a nice, easy to handle integral. So what do we get? We get 3/4, I guess. Oh no, this is just. Okay, so we got 3/2. Lovely. Lovely, lovely. Yes?
This reminds me of do we conventionally not choose to use polar or some kind of other like 3D coordinates with rotations because of non-regularity? I tried something in Uber,
Yeah.
and then it failed. I got the zero vector in one of the conventional ways. So do we usually have these?
Yeah, so so this is a nice thing. If we want to be really, really careful here, and being really, really careful is a good thing to do in math, this set of coordinates for polar coordinates is irregular at one point. It's irregular at 0. So if we want to be really careful, we should put strict inequalities here and here. And then we'll get that our thing is injective, it's nice, all this business. How does changing that to a strict sign affect the integral? The integral winds up being the same. So yeah, if we want to be really careful about injective and regular, we have to exclude the origin from our polar coordinates. Okay. Cool. Okay. Things people want to check on there? Things people want to ask about? All right. Onwards and upwards. Okay. Let's look at another surface integral. Okay. All right. What's going on here? All right. So check it out. This is one of these kind of like classic Stokes kinds of things. We've got this surface. It's like a sphere that is sort of cut or something. So let's figure out what the surface is. So we're going to start at height. So we're going to have a sphere of radius √2. Centered at 0, 0, 1. Okay, so this is going to be something like this. And then around that, we've got this sphere. It's radius root 2, so it's going to extend below the plane z equals 0. Then we're cutting off at height z equals 0. Okay, so this will be, this point up here will be 0, 0, 1 plus root 2. So this integral, right, if we wanted to integrate this over the surface directly, it would be a nightmare, right? This thing would be very hard to parameterize. You know, we'd have spherical coordinates. We'd be plugging into our exponents stuff like sine phi, sine theta. It would be a mess, right? However, Stokes says, don't worry about it. You don't need to parameterize the surface. You can just look at the boundary of the surface. Okay? And if we can parameterize the integral over the boundary, then life is good. Okay? So we need to figure out what that boundary is. Okay, so that's when we're plugging in z equals 0. So this is our favorite curve. This is the unit circle again. This. Okay. Okay, so to parameterize this, we can parameterize it normal way. Love it. Now when we apply Stokes' theorem, oh no, my pen is running out of ink. Okay, all right. Oh my god, what do I do without black ink? Maybe there's another pen? Huh? Right. Shiny pencil. Cool. Okay, so what do? We input our parameterization. Into our vector field. So this will be sine t minus cos t e to the cos t 0. Then we multiply that by our line element. So that's the derivative of this guy. And then 0. Okay, so check it out. This will turn into a 1, and that's fine, but it gets dotted against 0, so no big deal. Okay, so I get negative 2 pi. Things people want to check on, things people want to ask about. So Stokes saves us the difficulty of parameterizing this whole surface by letting us push to the boundary, which is nicer, generally simpler. But we can see that it goes both ways. In this one, we felt that parameterizing this curve would be tricky. Integrating this would be a bunch of sines and cosines, which would be messy. So we pushed to the interior, and this is the reverse. We felt that integrating on the surface would be complicated, so we pushed to the boundary. Right? Both of these are kind of productive moves. Both are helpful. All right. We're going to do sort of a nice little theorem. Then we're going to do the setup, I suppose, for the classification of conservative vector fields. Cool. So suppose that C is a closed curve that bounds a surface S. Oh, sorry, again. Okay. So we start off with a curve in space that bounds a surface, and then we're going to have some fixed vector. Okay. All right, so it's kind of the picture. Here's our curve, here's our surface. The curve is the boundary of the surface. And then the question is, if we have a fixed vector, so we're just always outputting V. The question is, what happens? How does this work? And Stokes gives a nice answer to this, right? So we can promote this up to a integral on the surface S. Now the curl of a constant vector, right? This is look something like this. And that'll be 0. So sort of one way to think about this is, there's a constant wind blowing in direction V. How much work do you do if you move through some path in space and come back to where you started? You'll wind up doing no work. As much as you push against the vector, against the wind in one direction, it will push you that much in the opposite direction. Okay, sort of a nice thing, sort of a nice application of Stokes. Think people want to check on? Okay. Onwards and upwards. Okay, let's state at least the setup of the classification, and then, yeah, I guess we can get into the proof. We probably won't finish it before the break, but that's okay. All right, so gradient vector fields, right? So ever since B41, gradient vector fields come up as being very special objects. They're like, direction of fastest ascent, fundamental theorem of line integrals, gradients matter. Right? Gradients are nice. In order to state the classification, we need a couple words. We need what is a simple closed curve. So we say that a curve is simple if, when we restrict it to the interior, it becomes injective. Okay, so it never intersects itself, it never bumps up against itself. So this is a simple curve. And then we say that a curve is closed if its two endpoints agree. Right, so simple closed curves are kind of things like, here's a picture of a knot. Right, this thing doesn't intersect itself, its endpoints meet, or we're going to have, another sort of something like this. Okay. Physicists like to introduce the following terminology, and we'll follow their textbook. We say that a vector field is conservative if it's a gradient. Okay, so that's just another word for something we already know. And we say that a vector field is irrotational if its curl is 0. Okay, so one way to think about curl is it measures how much the vector field is locally rotating, how much it is sort of spinning, and if that is always 0, then we say it's irrotational. Okay? So the classification goes as follows. It's great. We're going to need, okay, one second. We're going to need one piece of machinery. Okay, we're going to need something called Seifert's theorem. Okay, this is a nice, simple sounding theorem. Any simple closed curve bounds a surface. This is the kind of thing that I encourage you to try and write down a proof of it, because it turns out to be really hard. So this is a theorem from the 1920s. But yeah, it's the kind of thing that you're like, oh yeah, that's obvious. Wait, nope, wait, that doesn't quite work. And then you spend a weekend thinking about it. It's a nice term. We're going to need that later on in the proof of the classification, but here's how the classification goes. So suppose we've got a C1 vector field, then the following are equivalent. For any simple closed curve, we integrate to 0 around that curve. Okay? We behave kind of like that constant vector field V. Okay, so for any simple closed curve, we integrate to 0. For any pair of simple curves with the same endpoints, we have the same integral. Okay? I think this is the intuition of conservative. People are like, doesn't matter what path you take, it just matters the change in potential. Right, so the vector field satisfies the conclusion of the fundamental theorem of line integrals that these just depend on f of, okay, f of c of b minus f of c of a. Okay, great, so we satisfy that conclusion. The vector field is conservative and the vector field is irrotational. Okay? So what's remarkable about this theorem is that the first three things are hard to check. These are very, very technical to check. Okay? Right? These two rely on infinitely many paths. This one, it's hard to come up with a potential. Yuck. This last one is easy to check. Okay? So the last thing gives us a nice criteria for determining whether something's conservative. We take its curl, if we get 0, we're good. Things people want to ask about the setup? All right, let's bang out a couple of the easy directions, and then we'll save the second ones for after the break. Okay. All right, so for any simple closed curve, we want, so we're going to assume 1, prove 2, assume 2, prove 3, assume 3, prove 4, and form a cycle out of them. Okay, so let's suppose that we have this property. Now we want to take a pair of simple closed curves, or sorry, a pair of simple curves with the same endpoints. Okay, what we can do is we can form a closed curve by going along one and then going along the other one in the reverse direction. Okay. I'm going to put this in kind of like scare quotes because it's not really math notation. But yeah, let's look at what that looks like. Okay, so what do? We go along one, we go along the other, right? And one of them we have to reverse the orientation on, right? Okay, C equals this guy. Okay, so what do we get? Oh, aha! This page intentionally blank to continue the proof. Yes, okay. Okay, now we've written our curve C as the sum of two guys. One of them has the reverse orientation, and we know how changing orientation changes the value of the integral. It just gives us a minus sign. Yay, so we get the conclusion we want. We get that the path doesn't matter as long as we have the same endpoints. So there's the first direction. After this, we then have to go and produce a potential, right? We have to come up to go from 2 to 3, we have to produce a potential, then 3 to 4, we have to take curls of that. So let's take our break there. We'll take a break till 2:10. If people want to come up and chat, I'm happy to chat. And then we'll continue the classification. I'm going to just put a little note on the board. Sorry. What's up? Right, so if we need length 1, we're going to specify unit normal vector. So normal just means orthogonal, and then if we want length 1, we'll say unit. Yes, so in the divergence theorem, it has that outward pointing normal defined, and just before that in the notes, it gives the definition. And that definition is always going to have length, right? So I think this is the formula. That's what it gives. T's. And that always has length.
Are you sure that's nothing to do with
Yeah.
it? Should be a derivative.
Yeah.
field analysis methodology.
Oh, like contemporary now?
Yeah, kind of, because I'm thinking whether I would go to two
B43 is the math analysis course, right?
probably
Yeah. So as I said, so like so as I said at the beginning of Fourier series, almost half of analysis is Fourier series. Like the hard analysis that people are winning prizes for and doing important research in is kind of Fourier related somehow. Another part is like analytic number theory. That's a big area where you use tools from analysis to do number theory. But yeah, analysis is cool. Everyone should take it. Like it's a big idea. Yeah. I recommend taking B43. Yeah. Other things you want to check on? Yeah. What's up? Yep. So here's what I should say. It will cover the same content as the yes. Yeah. I always hesitate to say, will it cover week such and such and such and such? Because someone always gets angry at me. They say, but professor, there was a vector field in week 8, so it had week 8 material on it. And I'm like, no, but that was also in week 6. So I really, yeah, same topics as the original one, which were listed in the question by question topics. We don't know yet, so here's the process. So A22 and A29 have their term test tomorrow. So I want to make the deferred B42, A29, A22 at the same time. So I need to see who defers for A22 and A29. Once I have that list, which will be Sunday at noon, I'm going to send that list to the registrar. They're going to process it, figure out who's eligible, who's ineligible. Then they're going to give me a date and time. I'm going to ask them for the 14th, 15th, or 16th. And because it's Ramadan, I also wanted an evening. But they can't give me the time until I give them the list. Okay. So yeah, 14, 15, 16. Okay, great. There's it. Yes, it is. I can upload those tonight when or after class when I scan. Okay.
We're talking about the same time. Should we treat both C1, C2
Yeah. Yes. So yeah. So right. So right. So your sort of question is, what does same endpoints mean? I had intended something like this, like. Right, so that they match exactly the same thing. Yeah. Hey, what's up? Yes. Yeah. So So if you orient this clock, so yeah. So this is the counterclockwise. If you, exactly. Yeah. So that's my perspective on it. Yeah. I think that, so that this example I think is illustrative. This would be a very hard integral to compute on its own, but we can just push it to the boundary, and then the boundary is this. So my perspective is that Stokes, Green's, Gauss, all of them just let us move one dimension lower. It's like, okay, hard two-dimensional integral, easy one-dimensional integral. That's my perspective. But like, if you ask a physics guy, I don't include a physics people, but this guy always has good physics ideas. These things also have physical meaning. in like electromagnetism and stuff. I'm not a physicist, so I don't know really well. Sure. So the physics people, they're like, oh, you know, Stokes' theorem tells you such and such a fact about fluids. I don't really know this stuff, so I don't teach it. But it's worth looking into. Yeah, the other thing, okay, so A, they help us simplify things. B, another perspective for me is that they're forming this weird pattern. We've got fundamental theorem in one dimension, Green's theorem, Stokes' theorem, and then in week 9 we're going to do Gauss's theorem. And they all look kind of different. It's like, what's the pattern here? So for me, it's really interesting that there's actually one theorem that implies all the forms. No, that's called the generalized Stokes theorem. We're not there yet, but it's this kind of like, for me, it's interesting that each of these theorems is a term in some sequence or some pattern, and there's like big, probably the simplest answer is they make integrals simple. Gauss is, yeah, it's divergence over 3D. Yeah, we'll get there. Yeah, it's in the notes. Cool, cool. Okay, excellent, excellent. So let's pick it up. Let's carry on. All right, so we've shown the first implication from 1 to 2. Now we have to come up with our next implication that this thing is conservative. So we need something that this is the gradient of. Right? Okay, for all curves with the same endpoints. So our fundamental theorem of line integrals is saying that, this should be f of b minus f of a. Right, suggests the following. So what's kind of nice is that this gives us a formula that has our potential in it. Right, so this has our potential, and it doesn't exactly tell us our potential, it tells our potential up to an additive constant. Right, but that's not a big deal. If we take derivatives of an additive constant, no big deal. So what we're going to do is we're going to turn this into our construction of a potential. We're going to use this conclusion as something like our definition of the potential. Okay, so I need to tell you what the value at x is, but my integral doesn't really depend on the path at all. So what I can do is I can then build a path from the origin to x. Cool, so now we've got our definition, right? So what does this look like? Right, so our integral doesn't depend on which path we take. There's many, many paths that we can take. Right, there's one of them. Right, there's, I don't know, C, there's a straight line path. So this definition is very, very, very flexible. We can take any path we want, and we just have to prove that this F is actually a potential for big F. And we can, in our proof, we can construct any path we want to use. So what do we have to prove? We have to prove that little f is a potential of big F. So to do that, we're going to have to construct a clever path. Okay. So in order to do that, we need to say okay, so let's break this vector field up into its components. And let's write our function like this. So what do we need to show? We need to show okay, so we need to show that each of these derivatives matches. Okay, so how on earth do we do that? We need to construct clever paths. Okay, so what do? I want to measure my change in the x1 direction. So for I equals 1, what do? Right, okay, we've got this thing. I want to pick my path so that it will output my first component here. Right, so call this C1. Okay, in the n coordinate, go from 0 to xn. Sorry, which one? Sorry. I've been rambling a whole bunch, but yeah, we want to go from 2 to 3. So we want to say again? Where's 4? Sorry. Yeah. Oh. Yes. Sorry. Yes. Thank you. Yes, this needs to all be in dimension 3. So we don't have n dimensions, we've got 3 dimensions. Good. Love it. Okay, so we don't want to go like this. We want to be okay, cool. So now we can define this path like much more explicitly because we're only going in 3 dimensions. Okay, so what do we want to do? Okay, we're going to go 0, 0, t. Okay, then we're going to go okay, then what are we going to do? We're going to go up to x2. Okay, thank God that's so much nicer in 3 dimensions. Ah, beautiful. Okay. For sanity reasons, to make this not totally nuts, okay, I'm just going to add a little bit that these have to all be positive. Okay, so what on earth is this path doing, right? This is such a weird looking path. So we've got a point. Okay, what do? First, we go up to the right height. Okay, so we go up to, here, I should put it. We go to the correct height for this point. So that is C1 at x3. Then we go in the y direction. Go parallel to the y direction. That takes us to C1 x2 plus x3. Then we go parallel to the x direction. Okay. Why on earth would we construct this path? This is such a weird path. first, are people okay with either the math description or the picture of this path? You want to get somewhere. You want to get somewhere in a building, you go to the right height, then you go down the right hall, then you go down the right hall. We're moving one direction at a time. The reason why we pick this, I'll move this guy down a little bit. We pick this path because we want to prove something about derivatives, right? We want to prove that the derivative of f in the x1 direction is the first component of the vector field. So here, on this part of the path, nothing is changing. There's no change in x, no change in x. All the variation is in this last component here, okay? And that is only in terms of F1. Okay? So let's do that calculation. Let's take the derivative of this crazy function in the x direction. So we need to calculate how this thing changes in the x1 direction. Here, there's no change in the x1 direction in this guy or in this guy. The only place where x1 is changing is on this component. What do I want? This isn't what I want. Okay, so we go 0 to x3. Good. Okay, so now we can see sort of at the level of the notation that there's only one term here involving x1s. Everything else is independent of x1s. The only guy where there'll be non-zero business with x1 is here. Cool. Okay, so now we have to get the derivative of this guy. Right. Notice that we have this common term on top and bottom, this x3 plus x2. Okay, so let's integrate that on this range of values. Okay, now we also need the t derivative of our path. Our t derivative of our path is this guy. Right, so we've got this, we're just looking at this final segment. Here we're going to get a 1. Awesome. The work paid off. Love it. Very, very, very beautiful. Got a derivative of this thing. Got an integral. Those undo each other. We've only got one rate of change up here. Fundamental theorem of single variable calculus gives it this is F1. Yay. Okay. So people are like, what the hell? Where does this go? Why are you giving us this really, really long construction with all these details? I think there's a tutorial exercise at some point, right? So we chose this path, we calculated it out, we got that the first derivative is f1, but this was dependent on our choice, right? We really needed to really construct this particular C1. So in tutorial, you'll have C2 and C3. Okay, for the other two directions. Cool. All right, where are we next? So now we've got this construction worked. It gave us F1. Right, therefore this potential works. Okay, sweet. All right, now we've got to go 3 to 4. Okay, so what do? We say, suppose that we are conservative. Now we have to show that we're irrotational. That's not so bad. Okay, so at some point when we introduced curl, we did this calculation that gradients have to go to 0. The proof wound up essentially being equality of mixed partials. Okay. Love it. And now we have to complete the circle and go all the way back to the beginning to show that if we are a curl, then we integrate out to 0 on any closed curve. Okay, so now we are in the land of Stokes' theorem again. Right. So we need to show, oops. Right, we're here, and we need to show that for any oriented simple closed curve, we have that we integrate out to 0. Okay. So the tool that we need here is Seyfert's theorem. We need that there's some surface that this bounds. We can then apply Stokes' theorem to pull the integral off the curve and onto the surface. And we know that our curl is 0, so we're integrating 0 everywhere. Nice. So what do we got? We are conservative vector fields if and only if we integrate to 0 on every closed curve. Every pair of curves with the same endpoints gives the same integral. our gradient, and our irrotational. The hard step of this proof, the doozy step of this proof is this implication. Everything else is sort of pretty mechanical except for that step. Things people want to check about any of those 4 steps? Onwards and upwards. Okay. Oh my gosh. I gave myself 1 extra page and I needed like 3. Okay. For version 2 of the notes. All right. And maybe that diagram with that crazy path. All right. So we can now get the classification in the planar case, right? From our sort of power from on high, we have a classification in R3. This gives us a classification in R2. Cool. So suppose that we satisfy this. This isn't one of the assumptions we originally had, right? We don't have this thing. But let's use this to imply one of the things we know, right? This will give us, via Green's theorem, that we integrate to 0 around every closed curve. Cool. We integrate to 0 around every planar closed curve. That will give us our condition on endpoints. Or and then once we have fundamental theorem of line integrals, we then get that we're a potential again. So this is the 1, that's 2 direction. now we go back in the opposite direction. Reversing things, we want to say, suppose we're conservative, then we have to have this equality of mixed partials. Or sorry, no, we have to have this property of our partials. Notice that here we're C2. Right, so we really want C2 for this part. So suppose we've got the following. Which is what we wanted. Yeah, sure.
Oh, wait, because F, the vector field F is gradients.
Say again?
Okay, because I was comparing the thing with the previous
Yeah, so this is very similar to the proof. Very, very, very similar feeling kind of calculation. Okay. All right, that is a whole bunch of theory, but I love it. That's great. We don't often get to prove things in this class. Yeah, all right. All right, we've got two more thingies. The same vector fields. All right. So now we have a couple tools. You know, one of the tools that we can use to check if something is conservative is we can try and find a potential. Alternatively, we can check if something is irrotational. Oh, there's a Z missing. Yeah, so let's check that this thing's irrotational. Cool, I calculate out our cross product. Hopefully it goes to 0. So what do we get? We get x squared minus x squared. Then we get 2xy minus 2xy. Then we get 2xz minus 2xz. Yay, everything cancels out. Yay, the thing is irrotational. Okay. Notice that this doesn't tell us what the potential is, but it tells us that there exists some potential. Lovely. Okay. The other thing we can do to check if something is conservative is to find a potential for it. And finding a potential is tricky or annoying. One has to kind of stare carefully. But let's see if we can do it. Right. Stare at it. Ask ChatGPT. Ask your neighbor. Stare, stare, stare. It's tricky, right? It's like, how do I do this? So I think we're going to get xy cubed plus x plus y. I think that'll do it, right? We need a 1. X squared.
xy cubed plus x plus y. We will first integrate the first component,
Yep.
then the rest is just like, we kind of, I know we subtracted, but we take the derivative of y and subtract by the second component, and the rest is the differential only for y.
Yes. Yeah. Yeah. So we can. So there is a nice algorithm to this, right? We can integrate this guy in x, and then we can integrate this guy in y, and then we can figure out the constants we need to add. So let's check it out. Does this work? All right, so we get y cubed plus 1, 3xy squared plus 0 plus 1. Yay, it worked. Cool. Lovely. Yay! All right, we have a potential for the thing. Okay. So that is kind of the last thing I wanted to say about sort of Stokes' theorem, kind of classification. I'm going to say the sort of same thing I said at the beginning. Where are we headed next? So the last in our cycle of vector calculus theorems is Gauss's theorem. So Gauss's theorem is the kind of last variant we're going to see on this stuff. We integrate the divergence over a three-dimensional shape, and that's the same as integrating the vector field of the boundary. So again, we're derivative on the interior is the same as integrating on a boundary. So we'll play with that a little bit. We'll answer this question of what are the divergence-free vector fields? Well, it turns out they're the curls. So we'll answer that. There's sort of a tricky recipe there. Okay. We'll do a couple more calculations. We'll use Gauss to get volumes. And then we'll do this kind of cool thing about electric charges, which is sort of saying that Gauss also detects something topological. Once we're done those things, the course will escalate in theory again. So sort of the way the course has kind of been structured So sort of in the first 3 weeks, we did a lot of theory of Fourier, right? It was like very theory heavy, kind of very like meaty analysis, uniform convergence, this kind of stuff. So this is Fourier. I should say this is week 10, really. Then we kind of got into sort of like more calculation heavy stuff. And the last bit of the course is going to be differential forms. So the last 3 times I've taught this, people have said that we didn't do enough theory. There was a lot of like, what are differential forms? What's that all about? So there's going to be sort of more theory coming in the last 2 or 3 weeks. Okay, so this is sort of time, and this is proofs and theory and stuff. Okay, like the treatment of Fourier, our textbook. Okay, so our textbook does a terrible job of Fourier because there's no Fourier in it. There's just 0 coverage. Our textbook has a coverage of differential forms. I encourage you to look at that. It's very physicsy. It's very kind of like picture-based. In these last 3 weeks here, we're going to be using a reference by Tristan Needham. He's kind of the best author on this stuff. It is impossible to find this book online. If you Google it, you will never find it. There are no PDFs anywhere. That's a joke. So we're gonna do differential forms in weeks 10, 11, 12. Our last week of vector calc will be week 9, and then hopefully we'll have enough machinery that all these theorems that feel very different, right? Stokes, Green's, Gauss, hopefully they all become the same theorem by the end of the course, and that'd be really surprising and awesome. Okay, great. So that's where we'll finish off today. Thank you very much. I'm happy to take some questions. Yeah?
Write the thing down. Just want to verify. Simple as this, right? If we eliminate the plus C, that will give us this two.
Yeah, that's right. Yes.
I may have found a simpler proof from 2 to 3.
Oh, good. Great.
Yeah, could you just observe?
Yeah.
It's this idea that we can construct 2 paths, kind of. So we can kind of combine them together. At the very end, it's like the assumption, since the boundary or the path is arbitrary, the integrants must be the same.
Oh, I see. Interesting. Are there folks getting set up for a term test or something? Oh, so he. Okay, so we're getting set up for a term test. I want to take all these questions. I have time to. I've also got time to chat with you, but we've got a term test in here, so we're going to get out as fast as possible. Hey, good to see you, Sohi. Good to see you. Yeah, I'm going to just kind of like head out this way, and I'll be there in a moment once I erase the board and stuff.
Students sit down first and then we distribute. And this one is A. This one is A. Oh, I can do that.
Room PC. Okay.
Yeah, I can log in.
Shohei, if you have a
Yeah.
test, you can just come and kick me out. Just come in.
we have exam.
Yeah, no. Every prof would just get out as soon as they saw a test.
Actually, they give kind of signal, right? They kind of come early and kind of there, and I said, oh, do you have an exam? And I kind of finish early.
Sure, good, good.
Yeah, have a wonderful weekend.
Thank you, thank you.
So we go to U of T exam clock or something?
Yes.
Which one?
Exam timer. is
Exam
also will
timer?
come, yeah.
Oh, exam timer? Okay. Exam timer. Oh, timer. This one? No,
That's the
U
good
of
one.
T.
The first hint, that's the good one.
Oh, is it?
I like that one the most.
Oh, really?
Because it
Okay.
doesn't display seconds, which is kind of stressful.
Oh, I see.
So it'll display seconds for the first like minutes and then it stops displaying.
Okay. Just, 2 hours and 30 minutes.